In this video, I will explain a little bit more about what the sum of squares in an ANOVA setting means, right? So what we've learned is the total sum of squares is equal to the regression sum of squares plus the residual sum of squares, right? So that's the total sum of squares, and it's equal to that's the regression sum of squares, and that's the residual sum of squares. And if you think about this term a little bit more carefully, yi minus yi hat, that's actually the residual, right? So that's why this last term is called the residual, and then you square it, so residual sum of squares. From an interpretation standpoint, this represents the total variance in my response variable. This one over here, because it's a squared residual, right, that is viewed as the variance in the response that cannot be explained by our model. And this is the part that we say the variance in my response that can be explained by the model. So ideally, you want this quantity here to be as small as possible. If you want to solve this in a mathematical way, it works out only in a regression setting, right? So in regression setting, because we have least squares, so some of these terms will work out. If you solve this purely as a mathematical equation, it doesn't work out. It only works in the least square setting. So I'm going to draw some pictures just to illustrate what some of these represent. So let's again look at our scatter plot. My x-axis, my y-axis, and let's consider a scatter plot that looks something like this, right? And in this situation, right, the least squares regression line probably looks something like that: beta 0 plus beta 1 times x. So what these represent are the following. So let's also now suppose that we have the average value of my response variable. That's going to be a straight horizontal line, and maybe that's what this value is, y bar. So the total variance, what that represents is the following. It's going to be representing so let's take a look at this data point at the top right corner. So the vertical distance, yi minus y bar squared, is basically this vertical distance over here. So let me get the right one. It's basically this vertical distance over here, right, from the black point all the way to the blue line, right? That vertical distance is yi minus y bar. If I square that, and I do that for every data point, that's my total sum of squares. Now, the residual is basically the data point, the vertical distance from the data point to the red line. So if I square that, that's my squared residual, and I add all of it up. So this part represents the residual. The difference between the red line and the blue line, that is the regression sum of squares, right? If I square that, add it all up. So that's what these represent. So really, this vertical distance from the black data point to the blue line, that's the total variance. The distance of the black point to the red line, that is the residual. And the vertical distance between the red line and the blue line represents the regression sum of squares. And obviously that distance, you square that and add it all up. So that's really what this represents. So now let's consider the most extreme example where we have a perfect fit. Okay, so let me just move this picture a little bit on the side. So let's suppose we have this example where the data fits perfectly. Right, and so my regression line is perfect. In this situation, right, and sorry, the other thing I need to add, right, the average value y bar. So if you look at this situation, the distance between the black data point from the blue line is the same as the distance of my fitted value from the blue line. So in this situation, we have a perfect fit, right? We have SST being equal to SSR, right? Because the SS residual is equal to 0, right? The residual is the vertical distance between each data point from the red line, and in this case, with a perfect fit, that distance is all 0, right? So this is what happens with a perfect fit, and this is what happens when you don't have a perfect fit.